let's share some screens. Perfect. All right, so let's start off with this thing. Let me get the polls going here. Great, there we go. So this is hopefully a standard question. I think I even did one very similar to this in the videos, so it shouldn't be too crazy, I hope. And again, some of you might be like, oh, well, I could just plug this into a calculator. So like, maybe I'll do that here. And you could. I'd say try it first, try it by hand first, and then go plug it into a calculator. Because yeah, I can definitely ask you sort of tricky-ish questions about stuff like this. Yeah, I told her that everyone heard her, and now she's embarrassed. Okay, yes, I am back. And I'm gonna blame Connie, but not really. It wasn't your fault. No, that's not it. I was going to answer, but again, I have to like scroll through everyone to like when I want to direct message any of you, I have to find you in the list of students, and then Zoom randomly dies when I do that. So I don't know. Zoom make me so upset. There's another reason to go back to in person, so I don't have to deal with Zoom anymore. Okay, I'm going to call it in like 30 seconds or so here. Yeah, I mean, it could be worse though. We could be trying to do this in Microsoft Teams or something. No, what did I say? What did I say? Yeah, oh yeah, I hate Teams. Teams is terrible. Connie, yeah, you could totally do that. No, it's not about necessarily wanting to stay online. Like there are pros and cons to both. I'm not gonna lie, I'm getting a little tired of online though, because I've been doing this for, just like 2 years now. Nothing beats in person. Yeah, I would definitely rather go online. But I'm not gonna lie, I don't mind the commute or teaching online, right? Exactly, right? Like I said, there are pros and there are cons, right? And yeah, I'm just not generally. I'm kind of the pros aren't worth it anymore. Okay, yeah. So the class answered B with the majority, and then a little bit into D. So B is absolutely the correct answer. I think a lot of people said does not exist because if you just plug 3 into this, you get 0 over 0, right? And that's kind of an interesting thing. But it's important to note that the whole point about limits is, as a general rule, you just can't plug your answer in, right? Exactly, yeah, exactly. You're gonna have to factor it. So this is of the poll questions. This is question 9. Okay, and so it gave us the limit as x approaches 3, x squared plus x minus 12 divided by x squared minus 5x plus 6, okay? Okay, sure. So something to keep in mind is that when you're determining, like when you're trying to calculate a limit, you're never interested about what the function is doing at the limiting point. So in this case, we're not interested about what the function does at 3. We only want to know what the function does near 3, okay? So we want to know what the function does near 3, not at 3. Okay, so generally, if you go and you plug a number into your function and you get 0 over 0 out of it, that's not a sign that the limit doesn't exist. That's a sign that you need to do some sort of manipulation, right? So if we were to plug, so if we plug x equals 3 into this, we get 0 over 0, right? So again, that does not mean that the limit doesn't exist. That just means we have to do more work. So we have to do more work, okay? And what I want you to do is actually, if you go and you take a second right now, go pull up Desmos and plug this function into Desmos and see what it looks like, okay? And I don't know if Desmos is smart enough to give you the little hole at 3. And if you don't want to do it, you can wait and I'll do it right after. I'll try and graph it for you even for by hand. You'll see what this function looks like, okay? And you'll see that, you know, the correct answer is 7. So, okay, what we're going to do is we're going to factor the numerator and the denominator. Okay, so because the fact that we get 0 over 0 means that 3 is a root of both of these polynomials, right? That's what it means to be a root. If you plug a number into a polynomial and you get 0 out, that means it's a root of that polynomial. So I can factor both of these terms. I'm just going to rewrite out the question here. All right, so I'm going to factor it. And all right, someone double check my math here. So this is, I think this is going to be x plus 4 times x minus 3. And we knew an x minus 3 would come out, right? Because we knew there was a root. We knew 3 was a root. And if I do the bottom, it looks like it's going to be x minus 2 times x minus 3. And so we see that there's this x minus 3 term in both the numerator and the denominator. That's why we were getting 0 over 0. So we're just going to get rid of those. Right, that's just going to leave me the limit as x approaches 3 of x plus 4 divided by x minus 2. Now I can plug 3 into this. And if you can plug 3 into your number and you get something that makes sense out, that's not 0 over 0. If you can plug 3 in and you get something which makes sense, that's your answer, right? So if I plug 3 into this, now I get 3 plus 4, which is 7, divided by 3 minus 2, which is 1. So the answer is 7 like that, okay? Yeah, okay, so what you could do, Namir, if you don't want to, okay, so exactly. So if you, this is kind of an important point, Namir, so thank you for bringing this up. So you'll notice that I wrote the limit everywhere, right? Until I actually evaluated the limit. If you don't do that, your answer is wrong because the limit is a number and something like this is a function, right? So if you say, if you drop the limit here, you're saying a number is equal to a function and that's nonsense. If you don't want to track the limit though, and Rafid, I'll answer your question in a second. If you don't want to do the limit, what you would do is something like this. Okay, so don't do the limit until the end and say, right, so alternatively, just kind of do the work separately and then add the limit in. So say something like, notice that if x does not equal 3, x squared plus x minus 12, x squared minus 5x plus 6, and then you would repeat the work, and I don't have to carry around the limit because I'm not actually doing the limit, right? I'm just doing sort of the work ahead of time to simplify. Right, so now when you do the limit, and you could argue that there's still some redundancy here, right? Because I kind of have to replug this stuff in. But this kind of prevents you from having to carry the limit along with you everywhere. Right, Namir? So that could help if you want to do it that way. Like that just makes your life a little bit easier, and you could do it like that. Can we find other roots of this function? So when I factor it, I actually get all the roots, right? So the roots of the numerator are -4. The other root of the numerator is -4. The other root of the denominator is 2. On the other hand, though, if I plugged those numbers in when I was doing the limit, I would either get a limit of 0 out or a limit of infinity. So those ones aren't ones where we really have to be as careful. The tricky thing here is that I got 0 over 0, which was kind of meant that we needed to do more work, right? If you get 7 over 0, something like that, does not exist. If I got 0 over something, that would just be 0. So the only thing that we had to be careful about here was because we actually had 0 over 0, okay? So whatever x is approaching, will that always be included as the value when factoring? I want to know. So for example, what I could do, you could imagine, like this, you can imagine this question probably wouldn't show up on a test, but what if I said, find the limit as x approaches 1, like this, right? And the thing is, we're later going to learn what the word continuous means, but this is a function where you can actually just plug the number 1 in, and we would get 1 plus 1 plus 1 divided by 1 minus 3 is equal to 3 divided by -2, right? And so you don't factor anything out of this. It just it just worked out. So what you usually want to do when you're trying to, infinity over infinity is also kind of a tricky thing. So what you usually want to do is, your first instinct is going to be to try and plug the number in. And again, we're going to learn the word that allows you to do this. It's called continuous. If you can't plug the number in and you get something out like 0 over 0, it means you have to do a little bit more work, right? And you'll have to do some factoring. Maybe factoring is kind of the common thing. We'll see another question in a second where you have to do something other than factoring, but stuff like that. What if you have like a one-sided limit, right? So in that case, so for example, here, with the problem that we have in this question, approaching from the left or right actually wouldn't have made a difference. Okay, it would have been the same answer either way. If it were something like a piecewise function and we were approaching from the left, then what we do, like let's say we approach the x approaches 7 from the left, right? So if we had something like x approaches 7 from the left, then what you do is you assume that limits normally approach 7 from both sides, but in this case we're only approaching 7 from the left. So you assume that x is actually less than 7. Right? And then hopefully that will make a difference to your function, and you can do some sort of simplification and manipulation there. It's really going to depend on the function that you're given though, right? It's hard to kind of prescribe general things that you can do without knowing more about the function itself. Okay, then when does a solution not exist? Sure, let me do an example of that in a second. The limit can be 0. Okay, so everyone here, let's adapt this. Okay, so I'm going to take the same function, okay, but I'm going to change the limiting point. Okay, so let's do 2 things. So let's do the limit as x approaches -4 of this function. Okay, and when x approaches -4, let's try plugging x equals 4 into x equals -4 into this. What do I get? I would get 16 minus 4 minus 12 divided by 16 plus 20 plus 6. Well, yeah, that's 0. And that is the limit. Okay. So first of all, the limit can be 0. That's certainly possible. Or maybe let me write out another step here just so we can see what happened. Over, what is this, 42? So the limit can definitely be 0. And then here's an example of the same function where the limit doesn't exist. Okay, so if I plug this in, what am I going to get? I'm going to get 4 plus 2 minus 12 divided by 4 minus 10 plus 6. And that's going to give me 6 minus 12 divided by 0. And we would say, like, that's not actually a number, but we would say this does not exist because we know we can't divide by 0, right? So we'd say, oh, can't do this. So the limit doesn't exist. Okay, and the important difference here is this number up top is not 0. Right? So I can be confident that whatever this thing does, it doesn't exist because the numerator is finite or is not 0, but the denominator is. When it's 0 over 0, you don't know. Okay, when it's 0 over 0, it could still not exist. That's a possibility. Even when it's 0 over 0, it might not exist, but it also could exist. The point is that 0 over 0, you just have no idea. Right? You have to do more work in order to figure out what the answer is. Can I explain the first one again with the limit of -4? Sure. So in that one, I literally just plugged -4 in for the x's. Okay, so I got a direct message saying, can you explain the one with the -4? Just plug -4 in, right? So -4 squared is 16. And then -5 times -4 is positive 20 in the denominator. So I just plugged everything in and I got 0 divided by 42. And that's okay, right? We're not allowed to divide by 0, but 0 can be in the numerator. And so that gave us a limit of 0, and that's totally okay. Yeah, that should be +4. So if the numerator, yes, yeah, if we somehow still got another 0 over 0, we would have to manipulate again. So the first step is you plug it in, see what the limit is, and then see if you have to do more. Generally, yes. But Jack, in a little bit, we're going to learn the word, and the word is continuous, which allows us to determine if we were allowed to plug the number in the first place. But yes, as a general rule, the first thing you try and do is just plug the number in. If you get something meaningful out, you're done. If you don't get something meaningful out, then you have to do some more manipulations. Rafid, no, the first one is just 0. The second one you need to check. The third one is does not exist. For the last question, x approaches 2 is the answer, does not exist. Right, yeah, does not exist. When doing limit, should we also always solve the limit from the right and left? That's a tricky one. There are times when will say most of the time you can solve a limit just by doing both sides simultaneously, like you don't have to break it into two one-sided limits. There are occasions when you will just have to identify that doing it as a one-sided limit is the right thing to do. And that will often come when you're dealing with piecewise functions. It will often come when you're dealing with absolute values, things along these lines. Those are big hints that you probably want to break it into one-sided limits. But as a general rule, you should try and do two-sided whenever possible. Just, it saves you some work. When you say we need to check, how do we check? In what sense? Shanze, can you, where did I say we need to check? Because I probably would have said that about a couple of things. No, yeah, okay. So for the second one, do we need to check by factoring? Are there other methods? So for neither of these, do we need to factor, right? Like we just plug the number in, or sorry, yeah. So for this one, we don't have to, this one, we don't have to, this one, we don't have to. For none of these, do we need to do anything other than plug the number in. The only time where we have to do something different is when we get something that looks like this, or something like infinity over infinity. Those are the cases where we have to do extra work. The rest of the time, you can just plug it in. Mm-hmm. Yeah, 0, 0, but there are a couple of other cases too, right? Like there's infinity over infinity. Generally, there are a couple of things that are nonsense. But if the answer you get out isn't nonsense, then you're good to go, and that is the right answer. Okay. All right, let's do any possibilities that it's yes, 100%. Yeah, it could still be 0 over 0 after you factor it. And it depends on how much you factor it. So for example, here we're kind of dealing with polynomials, but there's no guarantee that what I give you is a polynomial, right? You can get 0 over 0 without factoring it. And then you have to do some other stuff, right? Like you have to do some more complicated stuff. Well, then you kind of have to use something else. Again, it's the techniques that you employ are really going to depend on the functions that you have. Okay, here, let me kind of get this one going, and I'll talk a little bit more. So, for example, here, hopefully you can all very quickly see you're going to get 0 over 0, right? And so as a hint, yes, you can do this one with factoring. Okay, it is possible, but maybe it's a little bit hard. It might be tricky to see what the factorization is, and so I'll show you another trick. But as a general rule, if your functions are polynomials, factoring it is a good idea. Right. Okay. Yeah. So there's this conjugate thing as well. Yeah. So with a square root, you can introduce a conjugate in order to basically the conjugate is secret factorization. So depending on how well they would have explained it to you in high school, the conjugate is just introducing the factorization. That's actually what's happening. So for example, here, I'm going to scroll up just for a second so people can see it. But question 10 of you can see this is question 11. Question 10 here. Oh, no, that's not what I meant to do. Why aren't you scrolling? Question 10 here is a conjugation problem. Okay, so if any of you want to try, maybe write this down quickly or snap a picture of it, give this one a shot too. And then in office hours, if anyone's struggling with this, we can go through it. Yeah, but I wanted to do this one. Why are these underlined? What is going on? Whatever. Oh, good. And now it's okay. I don't know why it's doing that. Computers hate me today. What do you think? Well, as like undo? No, yeah, it's not working. Oh, actually, it did work. 100% Curry to the rescue. Oh God, am I becoming that old man who needs the younger people to now tell him, oh no. Sure. And I mean, the secret of, I think, the younger generations is literally just knowing how to Google, right? Because, your parents ask you to do something and it's not that you actually know how to do it, you just know how to search for the answer. Oh, and by the way, yeah, I forgot to do it, but anyone, if you get a chance, go plug that last function, go plug that into Desmos. And then, so plug in the whole function, like the x squared plus x minus 12 and all that. And then plug in the simpler function after you do all the cancellation, and you should see something very interesting happen. Brandon, it's an interesting idea. There's a way you could do that, but generally no. It's an interesting idea. It's generally dangerous. To explain why it's dangerous, I'd have to get into a little bit more theory, but generally you never want to change the function you're dealing with, right? So if you add anything, you should add a 0. If you multiply by something, you should multiply by a 1. You don't want to actually change the function, because if you change the function, you change what the answer is, right? And then even if you like change the function, get an answer, and then undo the change, you have to be very careful about what change you made. So there are ways to make that work, but you have to be really careful about it. And just generally, it's probably safer to avoid it if possible. Do we have any tools to use for limit questions? Generally, the tools that you're going to be using are things like factorization. Like factoring is a huge part of doing these limits. Like again, you can do this with factoring. I'm going to show you a dirty little trick for this one. It's a very useful trick, but I'm going to show it to you, and then you can use it in the future if you want. And yeah, though, we're not going to spend too much time, you can imagine, actually computing limits in this class, just because, again, I will let you use a calculator and a computer to do all of these things. So for the most part, you could go and you could plug this into Wolfram Alpha or something and give you an answer. But there's a certain sort of bare minimum that I want you to be able to do in terms of computation, right? Curdy, exactly, right? So if you plug in both the function before the simplification and the function after the simplification, it's the same function, right? Now, actually, there is a slight difference between them, and Desmos might not show it, but exactly, there's a hole at whatever our limit was, -3 or whatever it is. There is a hole there, right? So Desmos won't show the hole. Oh, it does? Okay, so maybe there's a way to make it show up, but that's the only, right, okay. So yeah, there is a hole there in one function and there isn't in the other. And that's the only difference between them. Because we said, look, those, if you look at the algebraic manipulations that we did, they are the exact same function, except both of them have this x minus 3 divided by x minus 3 term. And that, just cancels out. So if you were to actually graph that function, you should hopefully be able to see that the limit is 7, right? Good, yeah, so Desmos isn't too bad. Okay, I'm going to close this up here in about 30 seconds. The class seems pretty confused, so this will be a good one to do. I definitely want to get one more question in after this, though, just because it will be very related to your writing assignment. So I don't want to spend too much time here. And of course, we can go into it a little bit more as well on the in office hours if people want. Right, and so one of the things you have to be careful about using computers as well is if you understand, for example, about how a computer actually graphs a function, it just computes the value of the function at a bunch of points and then connects them with a line, right? That's why in old school graphing calculators at vertical asymptotes, you'd see the line there. It's because it would just connect everything with a line. So that's why you have to be a little bit careful about trusting computers to do stuff, right? How do you write cube root in Desmos? I'm not 100% sure, but you could just do x to the power of 1/3, right? Because remember, the cube root is the third root. So that might be the best way of doing it. There probably is a way. I don't use Desmos enough myself to tell you, though. But like I said, there probably is a way. Yeah, no, it's not supposed to be complicated. And I mean, if you did it, great, phenomenal. And like I said, we'll do an example today and you'll be able to see if you did it correctly. We'll do something very similar. Okay, so yeah, that's absolutely a possibility too. Okay, so again, we can see in the polls, we're all over the place, right? Believe it or not, so the majority of the class did say B. B is the correct answer, so good job. Maybe you just plugged it into Wolfram Alpha, though. I don't know. Maybe, maybe not. Or maybe it was just guessing. Okay, so we want to figure out the limit as x approaches, what did I say, 1? X minus 1 divided by the cube root of x minus 1. So again, this is, 0 over 0, right? That's an issue. So again, if we plug x equals 1 into this, we get 0 over 0, right? And that's an issue. So we need to do some sort of manipulation. Now, some of you are going to be tempted to use the conjugate. And the reality is the conjugate is unfortunately not the right thing to use here. Let me see if I can explain it in a different way. Let me show you the slick trick first. Okay. So the slick trick first, the thing that I say is I almost want to do like a difference of cubes, right? That's sort of the thing that occurs to me when I look at this. So what I want to do is define a new variable, and you can do this too if you want. Okay, so what I would say is define u to be the cubed root of x, right? So that u cubed is equal to x. Basically, I want to get rid of the cubed root. The cubed root is really ticking me off. It's making everything more complicated than it has to be, right? I hate that cubed root, so I want to get rid of it. So I'm going to define it away. I'm going to create a new variable. It's going to be the cubed root. And then if I now change this equation so that it only has u's in it, there will be no more cubed roots, right? Now, the only thing you have to be careful about is when you define a new variable, you're changing the limit, right? So what we have to do is figure out if x goes to 1, what does u do? So as x approaches 1, well, in this case, that's not too bad. U is equal to the cubed root of x also goes to 1. Does that make sense? Right? Because in that case, we actually could just plug x equals 1 into u, and we know that it's converging to 1. So I'm going to now rewrite my limit entirely in terms of u. So we get the limit. Here, I'm just going to rewrite the question. X minus 1, cubed root of x minus 1. Now I'm going to rewrite it in terms of u. So u also goes to 1. Now x is equal to u cubed. The cubed root of x is just u, so I get this. Okay, cool, yeah. And this is so much better, right? Because these are polynomials. Like we can factor these, right? And it's not terrible. So this is, I think, something much better to worry, but it kind of requires us to recognize that we want to define away this cubed root. Okay, so now I'm going to factor the numerator. There's nothing to do in the denominator, right? It's already factored. So if you factor the numerator, you get that. We're going to cancel out the u minus 1s, boop, boop, like that. And you get the limit. And of course, Namir is very upset because I don't want to write down all the limits, but you got to do what you got to do. I can plug u equals 1 into this. Bam, we get 3. Okay. Are there any questions about that? I'll show you a different way. I'll show you, you can, let me show you how to do it with conjugates. So the problem with conjugates, right? The rule with conjugates uses this fact. Okay, here, let me show you what conjugate you would do. What did I do to u cubed minus 1? That's how you factor u cubed minus 1. Rafid, actually. I mean, probably most of you didn't spend a lot of time factoring cubes, but that's how you factor difference of cubes, right? I think you've all probably learned how to do a difference of squares. So if you think of 1 as being 1 cubed, that's the formula for a difference of cubes. Yeah, I would just look that one up. Yeah. So, and Ahmed, yeah, like same sort of thing. You probably just want to look that one up. Generally, x to the n minus a to the n is equal to x minus a times x to the n minus 1 plus x to the n minus 2 a to the power of 1. And normally we don't write a to the 1, but I'm going to do it so you can see what's going on. Okay, so this is how you factor a difference of nth powers. This is just a good formula to know. That's how I was able to do that so quickly, is because I know this formula. And this probably looks scary, but it's not, right? Because it's just like, notice the powers always add up to n minus 1. And then you just do all the possible ways that you could do it, right? So x to the n minus 1, a to the 0. And then I take one power off the x and put it on the a. And then take another power off the x and put it on the a. Another power off the x and put it on the a. And you just do that until you run out of stuff and you're done, right? Yeah, it's a nice formula. Okay, so there's, I was asked, how do we do this? Oh, okay, so importantly, here's the reason why conjugates work. Okay, so the reason why conjugates work is the idea of conjugates is you're going to write x minus a as the square root of x squared minus the square root of a squared, right? Which seems, you're like, why? Why would you do that? That seems really complicated. Well, because now if you use this formula, you would get the square root of x minus the square root of a times the square root of x plus the square root of a. And some of you might recognize, yeah, Simon, exactly. And some of you might recognize that this is exactly how conjugation works, right? Like you would see something like this, and then you multiply it, right? This is the conjugate, right? And the reason why the square roots disappear is precisely this equation, right? Exactly, you make it a difference of squares. So this is why conjugation works. This is the whole idea behind it. But you can see this isn't going to work with our cubed root of x minus 1. So the correct conjugate that we need to use here is we need to say, okay, so x minus a is equal to the cubed root of x cubed minus the cubed root of a squared, or sorry, cubed. And now use our difference of cubes formula, right? So this is going to be x to, this is going to be the cubed root of x. Maybe let me write them as powers. Maybe that'll be easier. So x to the 1/3 minus a to the 1/3, right? Times x to the 2/3 plus x to the 1/3 a to the 1/3 plus a to the 2/3. Okay, or cubed root of x minus the cubed root of a is the cubed root of x squared plus the cubed root of xa plus the cubed root of a squared. So if you're using conjugates, if you want to use conjugates, this is the correct conjugate, right? Yeah, so it gets complicated. So what you could do, you can multiply top and bottom. Okay, so if you want to do it with conjugates, you take this guy right here and you multiply it top and bottom with the conjugate. But, okay, no, but hold on, because there's another thing that we can do here. Notice, let me plug a equals 1 into this equation. So we get x minus 1 is equal to the cubed root of x minus 1 times the cubed root of x squared minus the cube, or sorry, plus the cubed root of x plus 1, right? So that's what happens if we plug a equals 1 into this. Well, what's the limit we're trying to do? Well, we're trying to do the limit as x approaches 1. And well, look at that. If it isn't how this question was made. Right? So you could do it that way too. And really what I did here, okay, but here's the thing. So many of you probably think the substitution that we did, up here that I'm going to circle in blue here is easier. The reality is these are exactly the same thing. Okay, they are exactly the same thing. It's just the bottom thing has a bunch of nasty cubed roots hanging around, right? But I still did the same thing. I basically factored a difference of cubes. And that's okay. Like if you're not comfortable with that, don't worry about it. Do the substitution thing that I did in the blue, but the substitution just gets rid of the cubed roots. At the end of the day, no matter how I did this, I still had to factor a difference of cubes, right? Like there really wasn't a way around that. Even multiplying by this terrible conjugate is effectively doing a difference of cubes, right? It's just kind of doing it backwards. And that's what conjugation is. It's making use of the difference of nth roots or difference of powers of n's formula. Okay. So yeah, just to give you an idea, you can imagine like I said, we're not going to spend too much time going crazy in depth with computing limits, but there was a time before, everyone had, a computer or a calculator where you had to know how to do this stuff. If X was not 1, could you still use the substitution? Absolutely. In fact, maybe let's change it a little bit. So let's say I did something like and let's see how the substitution would change. So let's say we did the limit as X approaches 8 of X minus 8 divided by the cubed root of X minus 2. Same sort of thing, right? Where we still get, 0 divided by 0. If we do it this way, so in this case, I would still do this substitution. So U cubed is equal to X. And the only reason I do that is because I see there's an X here, right, that I'm going to have to replace. But here's kind of the important thing. As X approaches, that's X, approaches 8, U approaches 2. Does everyone agree? So the reason why I really want to do this is because above X and U both approached 1, but here we can really see the difference where we might have to change the limit, right? So as X approaches 8 here, U approaches 2. So is everyone okay with that? Right, okay, so I got at least one person who wants me to go into it a little bit more. So basically what I'm asking is the limit as X approaches 8 of U, right, is the limit as X approaches 8. Well, what is U? It's the cubed root of X. This is one of those things I can just plug the limit directly into, right? So I would get the cubed root of 8, and if you figure that, it's 2. So when I write this, what I mean is I basically did this calculation, but yeah, okay, perfect. So now when I do the substitution, this is going to become the limit. Don't forget to change the limit, because if you forget to change the limit, it's not going to work out for you. U cubed minus 8 divided by U minus 2, right? And if you want to do that factorization, right, so we get U minus 2, U squared plus 4U, plus 2U plus 4 divided by U minus 2. Those things cancel. You plug into, you get 4 plus 4 plus 4, so you get 12. Okay. Oh, sure. So, right, U is equal to X to the 1/3. So U cubed is equal to X to the 1/3 cubed, which is just X to the power of 1. And the reason why I computed that is because I needed to be able to substitute, right? I have to replace all the X's with U's. So I needed to know, I already said, oh, the denominator has a U in it. If I want to replace X with U, I need to know how it's related. Yeah. Okay. Now, everyone, today is our 2-hour lecture anyway, but I want to, so I know you don't have anything after, but I really, really, really want to do another one of these questions, okay? Because I think they're going to be super useful for your writing assignments. So let me see which one, at least which one of these I want to do. Yeah, let's do this one. Okay, and again, if for whatever reason you have to leave, you've got a hot date or something in the middle of the pandemic, whatever, we're still recording, so don't worry about it. But hopefully you can hang around. If we use an online calculator to factorize, yeah, I think it's better safe than sorry, right? Is that you should just say, yeah, I used a calculator anywhere you did it, because you're allowed to, and it's easier than us being like, how did this person do this incredibly, maybe complicated thing? So I think it would be better. Yeah, okay, see, Aziz. So I think it's better if you use a calculator just to say that you do, because you won't lose marks for using a calculator, you're allowed to, and it keeps us from suspecting that you did anything weird, right? Okay, so this question is very similar to the writing assignment. If you haven't taken a look at the writing assignment, this question is worth doing simply by virtue of the fact that it is so related. Okay, so give it a look and see if you can come up with the answer. Yeah, you can. Yeah, absolutely. No, sure, you can use any kind of calculator. If you want to use Wolfram Alpha, you want to use a like TI-92, whatever you want. Sure. I mean, like, are you asking me to go back to that previous example so you can pick, because I'll post these problems tomorrow, so you'll have them. But yeah, if you wait, maybe let's finish this calculator and then I'll go back and I'll show you the thing and you can take a picture of it. I have like an 83, an 84, an 86, and a 92 plus. But here's the crazy thing. The TI-83 costs the same as when I was in high school, and I bought a TI-83. And that's insane for a couple of reasons. One, inflation should have made it go up, but two, the cheapness of transistors should have made the price drop, right? Like there's no way if I bought a laptop that was 20 years old, would it cost what I would have paid for it 20 years ago, right? You practically have to pay someone to take a laptop that's 20 years old. Those TI-83s haven't gotten more powerful. They're the same calculators that they were 20 years ago. And yet they haven't changed in price. They should have plummeted in price, right? Right, okay, so I got a question, which is why is it f of x and not just f of x, to make the question harder? Because if it was just f of x, you could do it by inspection, right? You could just look at the graph and know what the answer is. But here, it's a little bit, it's a little bit more complicated. Sure. Yeah. I mean, we can do a limit that doesn't exist on this graph right now. And yeah, I mean, I could show you it. In fact, I'm going to copy this this graph so I can show it in the next one. How do I do this again? Is it no, it's not Windows S. I'm sorry. A bunch of stuff's going to pop up on the screen for a second. There we go. Mm-hmm. Yeah, I think if you just click on polls, it'll reopen them. No? Well, guess, and you can direct message me the answer, and then I can tell you whether it was right or wrong. Ooh, maybe that'll work. Yeah. Yeah, I never used Zoom from the other end, so I have no idea how to use it. Ah, okay, sure. Well, same, that's not an option. Sylvia, no. Yeah, close, but not quite. Yeah, this one's a little tricky for sure. The dot is, so you see the hollow dots? So the hollow dots tell you that the function is not defined at that point. So for example, if you look at the dot at 1, right? So it's at 1 on the x-axis and 3 on the y-axis. You'll notice that there's a hole in the graph there. So that hole is the value of the function at that point. Yep. Yeah, Lilu, yeah. Okay, let's do 30 seconds here. Because there isn't too much math to actually do here, right? There's no computation that you can do. It's more of just explaining what the answer is. That's why this is a part of the writing assignment or similar to the writing assignment. Kind of specifically, is there like, what do you mean? Like what sort of limit do you want me to show you? Yes, this is a composite function. Oh, sure. Yeah, absolutely. Yeah. No, the holes are the function. Or rather the holes indicate that the function is not defined at that point. And then the dots are the point where the function is defined. So in this case, f of -2 is equal to 1 because the dot is the value of the function. Mm-hmm. Not 0 over 0, because 0 over 0 just isn't defined, right? Like it's not a number. So here, I'll talk about that quickly because this is an important enough point because this is how graphs are drawn that like enough people seem to be kind of bothered by what the holes mean. So we'll talk about that. Okay. So let's see how we did. All right, that's pretty uniform to suggest that pretty much everyone's just guessing. The majority of the class said C though. C is not correct. In fact, B is the correct answer, and it is the second lowest voted thing. Yeah, B again. Oh, you know what? I need to paste this in. So let's do that. All right. And let's maybe make this a little bit bigger here, just so we can talk about it. Nice. Okay. So everyone, the whole. Okay. So for this function, f of -2 is equal to 1. So what we're saying is, if we wanted to know the value of the function at -2, well, it's not this, okay? It's not 0, and it's not 2, because we can see that there's a little hole there, right? So the hole indicates that the function is not defined at that point. The dot here is the value of the function itself, right? And this height here is 1. So f of -2 is 1. Where's the other dot? It looks like it's at f of 1. So f of 1, it's not equal to 1. It's equal to 3. Okay, so does that make sense, everyone, for like what the holes are doing? The holes are telling you the function is not defined there. And then the dot is telling you what the value of the function is there. So this might look a little bit weird because usually we're not used to really discussing functions like this, but that's how we show them when the function has what are called removable discontinuities, which some of these are. Okay, and so for example, here you can see that doesn't show very well. So at 3 here, you can see that we've actually put a hole there to really solidify the fact that the function is actually defined at the end of this line, but not at this point, right? Because there's a hole there. Does that make sense? Is everyone okay about that? So if we're trying to find a value at a hole that is not a closed dot, do we just say, well, okay, it depends. Are you talking about limit or value? Because both of these are defined as values, right? Both of these, the function exists here. It's not that the function doesn't exist. The function absolutely does exist. Yeah, so the value, yeah, it does exist. Right? F of -2 is 1. It's not does not exist. It is 1. I mean, if the closed dot wasn't there. Right, okay, sure, yeah. If the closed dot wasn't there, so let's say this, let's see if I can erase it. So if that wasn't there, now f of -2 would be undefined. Yeah, it would be does not exist. Can we have both a point and a hole at the same time if the function is defined on one side but not on the other? Both a point and a hole. I mean, isn't that what 3 is? Right, where you have a point on one side and a hole on the other? Or maybe I'm not understanding what you're asking, Emma. As in it has the same y value. Okay, so yeah, I might not be understanding what you're saying, but just remember, so a function, remember, has to satisfy the vertical line test, right? So when you draw a vertical line, it can only hit the graph once. So for example, if I draw a vertical line anywhere any of these holes are, notice that it only hits the function once, right? And where does it hit? It hits in wherever the dot is. Right? So you can have any arrangement of holes and dots you want, so long as this rule is true. So long as when you have the vertical line, you only hit the function in one place. So when x equals 0, f of 0 is equal to, that's true. When f of -2 is equal to 1, so why is the answer not 1? I will show you. Yeah. Okay, perfect, perfect. Okay, so let's actually do the question now. So hopefully this clarifies like dots and holes and stuff. Okay, so now let's actually do the question. So let's do, we're doing the limit as x approaches, what are we doing? X approaches 0 of f of x, okay? And let me just, I assume you did not mean to unmute, so I'm going to mute you. Do hollow holes don't define the function? Right, yeah, exactly. The function's not defined at that point. But if there's a dot above it somewhere or below it somewhere, it means that that is the value of the function there. Okay, so what I want to do, so the question is, what is this equal to? So let's start by looking at the inside function. Let's look at, okay, I'm going to look at what I'm really thinking about the inside function here. So what is the limit as x approaches 0 of f of x? Just based off of this graph, what is that equal to? -2, great. But we can say more than that. What can we say? Right, specifically, it's coming from above, right? Oh yeah, from the right. From above, excuse me, / the right. Does everyone see that? Okay, so if it approached -2 from both sides, that would look something like this. Okay, let's try it. Let's try plugging in. Let's make a little table here. Okay, let's make a little table. So let's try a couple points, and we're just going to eyeball them, right? Like we don't know exactly what the function is, so we can't get exact numbers. But let's make a little table here. So we're going to do x is approaching 0. All right, here, let's do it like this. So x and f of x. Okay, and then I will zoom out so that we can see the graph. So we're approaching 0. So let's do something like 0.5, 0.1, 0.01. Okay, so based off the graph, somebody, yeah, exactly, f of x. Yeah, we didn't know more than that, right? We just were told that this was the graph of it. So based off of the graph, somebody eyeball me, what's roughly f of 0.5? Just get close. Yeah, it's about negative 0.5. Everyone agree, right? Like we're gonna go at a half, and we're gonna kind of go down here. Oh yeah, okay, that seems to be about -0.5, right? Okay, what about 0.1? So if I like go here and go down, right? What is that? Like maybe -1.5, probably a little bit more than 0.8, like maybe 1.2. I think the minus signs might be thrown. Okay, sure. Let's say negative like 1.7 or something. Okay, and then like it's pretty hard, but what would you guess f of 0.01 would be? Yeah, something like that, right? Exactly. Okay, so -1.99 or 1.9, something along these lines, right? Okay, let's try this again. This time, let's do the negative. So -0.5, -0.1, -0.01 f of x. Okay, so this time we're hanging out on the left-hand side. Let's do maybe, here's a half. We go down and something like that. What is that? Roundabouts. Yeah, it's really close. Sure. Yeah, -1.8. I like that. -1.8. Okay, if we did 0.1, -0.1, what do we get? We were down here. Like at this point, they're just getting really, really close to 0, right? Yeah, -1.9. And then maybe like -1.99 again, something like that. Okay. Yes, Dad, I like it. It's very precise. I love it. Okay, so notice, so both of these are approaching -2, right? Our numbers are approaching -2, but they're always bigger than -2, right? And don't remember not to be thrown off by the negative sign, right? All of these numbers are bigger than -2. Does everyone agree? right? Okay, so all these numbers are approaching -2. So what that means is that we have, right, f of x is approaching -2, but it's approaching from the right. So what we're going to do is when we do f of x, x approaches 0, f of x, well, we know that this inside thing is approaching -2 from the right. So why don't I define basically a new variable? Let's do something like let u be equal to f of x. So as x approaches 0, u approaches -2 from the right. And our limit here becomes the limit as x approaches 0. Well, let's change it right to u. Let's just go straight to u. U approaches -2 from the right of f of x. It's from the right or from above, right? So from the right means that the number is always bigger than -2, right? So the number is always a little bit, right? That's what the plus means. So it's always a little bit bigger than -2. Notice that it's not approaching from both sides because there's no number that's less than -2, right? You don't have to use u. You could use something else if you want. V, S, T, alpha. Well, in this case, there are examples where we could have done left, but this example is just only from the right. But there are examples where we would say left. Right, okay, so why does that matter? Okay, so let's go back up here. And so let's look at f of x. So again, this is the graph of f of x. What is f of x doing as u approaches -2 from the right? So we look at it from an up and down perspective, but just note it as left and right. Yes, yeah, exactly, yeah. Yeah, and some people say, approaches -2 from above or -2 from below. If you prefer above and below instead, some people definitely say that. Okay, so looking at the function, what is, this should be f of u. What is our function doing as it approaches -2 from the right? It approaches 0, right? It's doing this, white is a bad color. It's doing this thing. Sure, yeah. It's from the right because, okay, so let's talk about what to the right and to the left mean. So I've got the number -2 here, right? Or maybe here, let me say this. Let's draw a number line. Here's -2. These are the numbers to the right. These are the numbers to the left, right? But the problem, of course, is that our number line is actually the y-axis, right? So when I have the y-axis and I've got -2 here, this stuff here is the right? It's the stuff that's bigger than -2, and this stuff here is the left. It's the stuff less than -2. Does that make sense? Right? So the problem with between like right and left maybe are a little bit confusing here because when we're looking at it, we're looking at the vertical axis and we're saying, are we approaching -2 from above or from below? But when we turn that horizontally, it becomes from the left and the right. So above and right mean the same thing, and below and left mean the same thing. Yeah, you're right. I should say from the left, maybe is better. From the left and from the right. If we were to approach -2 from the left, it would be +2, right? So if we approach -2 from the left, it would be this one, which would be +2. When both sides is larger than -2, we say f of x would approach -2 from the right, yeah. But what if one side of f is constant? Ooh, yes, that's a great question. That is a great question. I.e., what is the limit as x approaches 1, right? Lead, like that's exactly your question. Is the limit as x approaching 1 is exactly that problem. So let me address yours in a second. Let's just make sure everyone's okay with this, and then I can show you because we actually have that problem prepared. Okay, but everyone, let me maybe give you a different perspective of this as well. So again, what if we did a table? Okay, so I'm gonna have to do this up here because I need you to see the graph. Again, let's do this from a table. Okay, so let's do X is 0.5, 0.1, 0.01. And now we're going to do f of x, right? Okay. So, or maybe actually, let me make two parts to this table, f of x and then f of x, right? And so we said this is like negative 0.5. This was, what did we say? Negative 1.7 and negative 1.99. Okay, now in order to figure out what f of x is, I'm going to take this number and I'm going to figure out what the value of the function is at negative a half. So if I go to negative a half, which is about here, right? What did we say that was? About negative 1.8 or something, right? Okay, let's do the next one. So let's do negative 1.7. So if I do negative 1.7, that's about here, right? And that is what? Maybe about a half, let's say, or negative a half. And then we said negative 1.99. And that's about here. And maybe that's, I don't know, negative 0.01 or something. Okay, so does everyone agree f of x is approaching 0 from this side? Does that make sense? Okay. Do we want it? Let's do the other table now too. So let's let x approach 0 from the left-hand side. So negative 0.5, negative 0.1, negative 0.01. And what do we say these were? 1819, 199. Okay, and we've done some of these already, like, right? Like 1.8 is like here, negative 1.9 is here, negative 1.99 is here. Notice it's approaching 0 still. X has positive values. So shouldn't we use the values on the right side of the y-axis? I mean, I am, right? Like that, these are values on the right side of the x-axis. Right, yeah. So this table here is x is approaching 0 from the right. This table here is x is approaching 0 from the left. And in both cases, f of x is approaching 0. How are we feeling? Okay, so for just for the function, so if we do the limit of just f of x as x approaches -2 from the right, we're saying, okay, we're approaching this point, but we're only coming along the function to the right of this point, right? So we're going to completely ignore this stuff. And we're saying, what is the function doing? Oh, well, the function seems to be limiting to 0 like that. Is what from the left? These numbers in the middle column here are all to the right of -2. Right, okay. Okay, cool. Is everyone else okay? Are there any outstanding issues here? Because Lee brings up just this beautiful problem that I want to talk about. So this is the second table, which is from the left, is still coming from the right. Well, it depends what you mean. Yes, it is coming from, it's approaching -2 from the right. Yeah, it's not on the left at all, right? Remember, left is relative. We're talking relative to -2, right? These numbers are like, what, -0.5, -0.5 right here, right? Relative to -2, these are to the right of -2. But what happens if the inner limit gets approached from the bottom and taught from the right? Well, it depends. It depends on the graph. In this case, the answer would be does not exist. Why is the answer B? I'm stuck after getting -2. So B, the answer was 0 because, okay, let me see if I can explain this another way. Yeah, let's see. I've been using a table of values. Yeah, I don't really have another way. Let me think. Okay, so direct messenger who says, my answer was C. Can you tell me specifically why you think it's C? Because like if the answer was f of -2, you would be right. Okay, so f of -2 is equal to 1. That corresponds to C, right? But the function isn't asking us what the value of f at -2 is. It's asking us what is the behavior of the function as we approach -2, right? So in this example up here, okay, so we have down here, we're going to have the limit as x approaches -2 from the right of f of x is equal to 0, okay? Because remember, we're always sitting to the right of -2, so we're only doing this. And if we approached -2 from the left, we would actually get +2 because we would be approaching like this, right? Does that make sense? So when you say you're, okay, cool, yeah. So when we say we're approaching -2 from the right, we only look at what the function is doing to the right of the point. When we say it's approaching -2 from the left, we only look at what the function is doing to the left of the point. And so that's how we figure out what the limits are. Yeah, exactly. So because in that intermediate step, we were approaching from above, exactly. It becomes now from the right, exactly. That's exactly it. Awesome. Oh, yeah, no problem. Is everyone's good? Because now there's another great question about this that I want to show you, and because it's going to hurt your brain a little bit. I almost don't want to do it because I think it almost gives too much of the writing assignment away. Let's see here. Which one of these do I want? So exact same curve, right? Exact same function. Is this the one I want? So the limit as we approach 2. No, that's no fun. There we go. The limit as we approach 1. Why do we look at x equals -2 for that question? So when we were approaching, in that original question, we were approaching 0, right? So we want to say, what does f do? And this is the same function, right? Exactly. It's because the f of x. So the inside f of x, right? The first f of x is approaching -2, and that means that the outside f of x, we're going to look at what happens as we approach -2. Exactly. If there's a straight line like y equals 2, and we get a limit is 2, we get the answer. Maybe. I mean, I think this is like, this problem is your question, isn't it? Asking about the straight line, because like we're approaching x is equal to -1. So in this case, we do have a straight line from the right. Yeah, sure. If you actually want to reset. Yeah, Rafid, absolutely. That's true from the left, right? But you have to be more careful about this time about what happens from the right. Okay, so really break this question into what happens when you approach one from the left and what happens when you approach one from the right, okay, and do them separately. Gerber, yes, but give me a little bit more detail in your explanation because I don't like your answer is correct. I'm not as convinced by the explanation just because there's two parts to this as to why it's that answer. And I just want to make sure that you have both parts. And it's not that it's not that it's undefined. It's just that it's somewhere else. Right? There's a hole there, but there is a dot as well above it. Well, maybe, I don't know. I mean, like, if that's the totality of your answer, then yes, there is more to it. No. Nope. Yeah, this one's trickier. Like, I think many of you have probably the right idea and are using the same techniques we used from the last one. And that's great. Like, that's phenomenal. But this one does have a second trick and it's specifically why we have this question, because the limit from the right is trickier. Like here, let's even kind of think about it while we're going. As I approach one from the right, what is the limit equal to? Right, it's equal to one. I think everyone agrees, right? Like for just the function, not the double composite, but just for the original function, as I approach one from the right, it's equal to one. Right, but does it approach from above or below? Right, Ariana, exactly. And it's just constant, right? It doesn't approach from either one or below. It is one. It doesn't approach one, it is one. So what does that mean? Not infinity. What's just one? Well, so the limit is one, but you say more than that. Which limit? Of f of x or of f of x? I mean, I'll do it with explaining it. I'll do it more when we actually take it up, which will be in like 20 seconds here. No, because what does the function do when you approach one from the left? Also one, but this time it approaches from right, approaches one from below. So, okay, let's take it up. Okay, so lots of people said B. Unfortunately, B is not correct. But that's good, right? This is the right place to be wrong because that way we get it right when we do like tests and stuff. Okay. So we're going to do the same sort of thing. This time we're really going to break it down, piece by piece, right? Yes, that's exactly what it is. Okay, so let's do what happens. Let's start with the easier side. So the easier side is what happens when x approaches 1 from the left. Okay, so let's do this case. So we said that as x goes to 1 from the left, f of x goes to what? So I made you already say it. I guess enough of you wrote it. It goes to 1 and it goes to 1 from below, right? So from the left. Everyone agree? Everyone's okay with this? Okay. So this means that when I do the limit as x approaches 1 from the left of f of x, remember, when you do this in a writing assignment, you have to say more words. Okay. How? Sure. So we're approaching 1 from the left. Okay, so we're approaching 1, right? So here's 1. We're approaching from the left. So I want you to forget everything on the right-hand side. Okay, don't even look at this stuff. If we just follow the function, where is it going? It's going to 1. Does that make sense? Right? So ignore everything to the right. Don't even look at the function over there and just say, what is the function doing? So it's approaching 1, but it's approaching 1 from below, not from above, not from both sides, just from below. Is that okay? Well, in this case, it's literally from below, right? Like if the function was something like this, it would be from above, right? But basically what we're saying is, yeah, the function is approaching 1, but the function is entirely beneath 1, right? It is beneath the number 1. So it is approaching 1, but it's approaching at it from beneath 1, right? Not from above 1, but from beneath 1. Does that make sense? Right? Like the function is beneath the number that it's approaching. So that's why we say it's approaching from below. Yeah, okay. And below, when you translate that to a limit, is the same thing as left, right? Below is the same thing as left, and then above is as right. And Connie, I'm not certain what you're asking. So will it be above and from the left? So remember, below is left, right is above. And maybe you're asking something about a different part of this question. So if it were above, it would be from the right. Exactly. Yeah, exactly. Okay, so f of x approaches 1 from the right. So that means that the limit as x approaches 1 from the right of f of x is the same thing as the limit as x approaches 1 from the right of just or from the left of f of x, which is equal to, as we said, just 1, right? Yeah, 1 left. Okay, everyone's good with that? Is that okay? So basically, it's almost as if it didn't really make a difference because we still got 1 from the left. Okay. Now here's the trickier part. So now let's look at x approaches 1 from the right. Okay. So again, this time what we're going to do is we're going to forget everything to the left, right? We're going to ignore all this stuff that doesn't exist. And we are going to approach 1. So I think we all agree that as we approach 1, so does the function, right? Exactly. So as x approaches 1 from the right, f of x also approaches 1, but it neither approaches 1 from the top or the bottom, right? It just is 1. So it's not even that f of x approaches 1, f of x equals 1. Does everyone agree? The value of the function as we approach 1 is just equal to 1. Yeah, but you're not worried about an open dot. When you take a limit, you're not worried about what the function does at the point, just what it's doing as it approaches, right? So you never care about what actually happens at the point just as you approach the point. Is that okay? right? And let's try it, okay? Here, maybe we can try it with a couple of table values as well. What is f of 2, right? So I'm asking you here, let's take this. What is f of 2? Well, it's just 1. What's f of 1? Oh, careful. What's f of 1? F of 1 is 3, right? Right? It's this thing up here. Right? Okay. What is f of 1.5? Okay, I like that. I think that was an oh yeah, you got like in the direct message. I got a direct message where I hope is a revelation. What is f of 1.5? What is f of 1.5? Right? 1.5 is about here. Okay, yeah, it's 1. So f of 1 is 3. Okay, what is f of 1.1? Right? Can you just write down what the answer is? Can you tell me what it is? Yeah, it's 3, right? And so the limit, what's the limit as x approaches 1 from the right of f of x, right? What are these things doing? It's just 3. Yeah, the limit is 3. Exactly. And as Brandon says, this does not agree with the limit we found from the left. So the limit does not exist. And my pen just died. Right? So the limit as we approach 1 from the left is 1. The limit as we approach 1 from the right is 3. Therefore, the limit doesn't exist. Sure, yeah. Okay, hold on. So there's 2 things I got to do here. Let me do the right first. Well, so notice, look, no matter what number, do you agree with all these calculations, Curdy? Like that, all these ones? Right? Well, okay, right. So as I approach, so do you think it matters if I change 1.1 to 1.0001? Right? Like probably not, right? Like it seems right. So it's just constantly the function 3. So if I ask you what, I basically am giving you a constant function 3, and I'm saying, what is that approach? Well, there's only one thing it can approach, right? Like what are these numbers getting closer to? Right. So that has to be the limit, right? Like it doesn't matter how small I make this thing, 1.00001, right? That's still going to be 3. So as 1 is like, as I'm getting closer and closer to 1, I still just keep getting the number 3 out every single time. Well, so it's not even, so I got a direct message saying, how are they approaching 3? It's not even that they're approaching 3, they're just equal to 3, right? And the way that they're equal to 3 is like, let's look at the graph. So again, let's look at like f of 2, just because it's really nice. So here's the point 2. So f of 2 here is equal to 1, right? And so if I say, well, what is f of 2? Well, I just said f of 2 is equal to 1. So I'm going to plug that in there. So it's equal to f of 1. What is f of 1? So that's this point, right? And oh, there's a hole here. So I'm not going to look at the hole. Ah, here it is. There's 3 right there. Right? This is equal to f of 1. Okay. No, the answer for this question, Connie, was does not exist, because the answer, the limit from one side is 1, the limit from the other side is 3, and because they don't line up, the two-sided limit doesn't exist. So the limit does not exist when the limit from the right does not equal. Yeah, exactly, Emma. Exactly. Perfect. Yeah. Yeah. When if the limits do not agree, the limit does not exist. Exactly, Christian. Yeah, we ignore the hole. So if there's a hole there, the function isn't defined there. So you have to find where the function is defined, like the point at 1 that's actually filled in. we get Brandon, yeah, I mean, like, I don't remember exactly what the graph was, but presumably if you did that correctly, and it's the exact same principle. So as long as you did that correctly, it should work out. So Agam, the previous one is in the like 14 or whatever. So not this one, but the one from before. This is 16. Is it possible for a limit to be defined if there are holes? Absolutely. Yeah, Emma, great question. So, and in fact, actually, this is a great opportunity for me to do this. Emma, this function has a hole at 3. Okay, so graph it and maybe plug it into Desmos. And as some of the other students were saying, if you actually put your mouse over 3, Desmos will say undefined, and that means that there's actually a hole there. So this function actually has a hole at 3. Nonetheless, we found that its limit does exist. Right? In fact, maybe I can show that. Well, okay, hold on. Let me do Agam first, because I think there were more. The limit is we approach 0. Agam, that was the one. Okay, sure. Here, let's and same. I think that this will answer your question as well. Let's redo the previous one, but maybe instead of doing 2 sides, let's just do 1 side. Okay, so let's break it into 2 one-sided limits. So let's again. Let me just copy this in. And okay, so again, let's do this one, but maybe let's do it in a different way. So again, let's do the limit as x approaches 0 of f of x. Okay, so again, I'm going to break it into 2 cases. Let's approach x, or let's approach 0 from the right. Okay, and same, hopefully, again, this answers your question. So let's approach 0 from the right. Okay, so when I approach 0 from the right, I'm kind of forgetting everything that happens over here, right? And so as x approaches 0 from the right, f of x approaches -2, but it does it from above, right? Does that make sense? Is everyone okay with that? Because Agam saying this is really for you too. Okay, perfect. So x approaches -2 from above. Okay, so now when we do f of x, we're going to approach. So now when we do the limit as x approaches 0 from the right, f of x. Okay, so we said that this thing approaches -2 from the right. So this limit is going to become the limit as x approaches -2 from the right, f of x. And if we do that, that's this bit right here. It's because the line is above -2. Yeah, exactly. Right? Right. So again, we're approaching now -2 from the right. So we ignore all of this stuff. What is the function doing? It's approaching 0. It's actually approaching 0 from below, but because we're not doing another composition, we don't have to worry about that. So it's approaching 0. Are we okay with that? That's good? Okay. Same? You're good? Okay, no, if you're confused on this step, we got to do it. Okay. All right, so remember, we're doing a double composition, right? So we're trying to figure out the limit of f of x, right? Right, okay, exactly. So basically what I'm trying to say here is when I do the limit, here, maybe let me write this a little bit bigger just so I can kind of like label it. So we've got the limit as x approaches 0, f of x. Okay, now remember when you evaluate a composition like this, you do the inside first, right? You have to figure out what the inside is doing before you can plug it into the outside function. So what we want to do is we're trying to figure out what, actually, maybe let me draw this in yellow. We're trying to figure out what the f of x on the inside is doing as x approaches 0. Okay, so over here, we said, okay, what is x? What is the function doing as we approach 0 from the, oh, sorry, we're doing from the right here. What is it doing as we approach 0 from the right? Well, let's ignore the function. And we said, okay, so as x approaches 0, f of x is approaching -2, but from the right. Okay, right? And I think you said you were okay with that part. So you're still okay with that, right? And hopefully the color coding here will help it a bit. Okay, cool. So what I'm going to do now is say, okay, well, this thing, okay, this yellow thing inside here, that's approaching -2, but from the right. So if I were trying to figure out what this thing did as the inside is approaching -2 from the right, that's the same thing as just doing x approaches -2 from the right of the single f of x. Or if you want, what we could do is we could say u is equal to f of x, and our limit becomes the limit as u approaches -2 from the right of f of u. Okay, and that f of x part, that internal f of x, is the yellow thing. I've tried to keep it like color coded consistently, right? So everywhere where we used the fact that we were approaching -2 from the right, I've tried to keep that yellow. So does that kind of make sense? Like how, right? Because we don't want to deal with f of x. That function is really hard. I have no idea what f of x looks like. But if we figure out what the inside is doing, maybe I can use that to figure out what the whole function is doing. Show what on a graph? Why doesn't it become f of -2? Because we're not, remember, limits only care about what happened when you're nearby, not what happens when you're actually at the point. Okay, so I approach -2 from the right. Here, and then when I plug that back into the function, that means I'm going to approach -2 approaches 0, and from below, but you know, that doesn't really matter for this question. Okay, so Josefa, that's great. Okay, perfect. Isn't what below? F of x? Yes, f of x is approaching -2 from below. No, okay, be careful here. When I say I'm approaching 0 from below, -2 from the right. Yes, because I'm approaching -2 from above. Did I say -2 from the left at all? Yeah, we are approaching -2 from the right. Or from above, right? Right and above mean the same thing. So we're approaching -2 from above. Oh, sorry, if I said below, yeah, I apologize. So we're approaching -2 from above or from the right. That means that f of x is approaching 0. It's approaching 0 from below, but again, the below part there doesn't actually matter. Yeah, if I can wrap this up pretty quick, Jacob, I think I can still do it. I really want to make sure people are okay with this one. And then if not, Jacob, you can throw it on Piazza. Like you can try and come up with an example of it. We could talk about it on Piazza. This is a one that's nasty to do on Piazza though. So I kind of rather try and make sure everyone's okay with this in person still. Okay, are we good with that? Same, are you okay? Okay, you're good. So now, so that's one side, right? And if we now do the other side, okay, so maybe I'm going to try and move this stuff over. So it's together. So that stuff's kind of like over there. Okay. So now as the second case, so now let's approach 0 from the left. Okay. So I'm going to delete all this stuff. Okay, so if we approach 0 from the left, we're coming in like this, right? And so here now, f of x is approaching -2, and again, it's approaching from above. Okay, sweet. Yeah, if the u substitution works, that's phenomenal. Yeah. Okay, so we're approaching -2, but still from above, right? Does everyone agree, right? Like it's still coming in from above. And so when I plug this back into the function, f of x is still approaching 0. Okay, and then in terms of the u substitution, we've got the limit as x approaches 0 from the left, f of x, right? We're going to let u be equal to f of x, so u approaches -2 from the right. And notice that this just really becomes exactly what we had before. U approaches -2 from the right of f of u. I should have put my brackets in first. And that's equal to 0. Yeah, it's still from the right. That's the important point in this question. It's still approaching from like, or we're approaching -2 from the right. Okay. Everyone okay? So since the limit is 0 from both sides, the limit exists and it's 0. Exactly. Yeah, the limit exists from both sides. They're the same. And so the two-sided limit also exists and is equal to that number. Okay, perfect. This one, everyone, I really recommend, especially if you really struggled with this and it makes sense now. This is definitely something that in the 5-10 minutes or so after we finish lecture here, you should write yourself a little note explaining this, because especially if you really struggled and it's starting to make sense now, you might have lost it by tomorrow, right? So we finished lecture here today, even if you want to take just a couple minutes and take a break, whatever, but make sure shortly after, take a picture of this question and then write yourself a little bit of a note. So that way, when you're looking at this in a day or two from now, you remember sort of the explanation that came here. I mean, you can watch the video and everything, but nothing will be better than you writing it down in your own words, okay? The first one, the answer would have been 0, which for this question was B. I mean, I can try and do this tonight. Yeah, I mean, it just takes, it takes like 45 minutes for the video to compile, and then I have to upload it, and then I have to link it. So that takes some time. Almost always it's up by Friday, right? So the inner f of x is the same for 0 left and right. Exactly. Yeah, they both approach -2 from the right. So the limit of f of x depends on when f of x approaches. Yeah, absolutely. Yeah. When will the poll questions be uploaded? I usually do it tomorrow. Yeah, I usually do it like at 2 or 3 p.m. or something on Friday. So yeah, they'll be up pretty quick here. And if I'm quick, I'll do it tonight, but we'll see. Okay, so Jacob wanted me to do an expected value question quickly with a loaded die. I want to do that because I think he's been very patient. Can you download and clip the page you wrote in the chat? I think I've posted this OneNote sheet for people to see, but check it out, see if it's up there. But I can do it if it's not up there. Just maybe send me an email tomorrow if I forget. But I think I've actually posted the entire OneNote document thing for you to do it. And yeah, Josefa, thank you if that works out. Okay, let me try and do a loaded die question really, really quickly. Said 421 had what are you doing to me? Zathra, please don't do that. Okay, dice is a little bit tricky to do. Okay, so yeah, if we try and make a loaded dice question, what can we do? So we've got a blue, let's say fair blue die, and then a loaded red die. And then let's say the red die has this probability distribution, 1/9 if X is even, and 2/9 if X is odd, okay? Yeah, coin would be quicker. I think maybe we should do, well, I mean, but I think, Jacob, okay, you said, okay, I can do a coin. Yeah, coin would be easier. But I also don't want to give away the problem we were doing in the thing. Let me see if I can maybe think of a better one. See, Ariana. Okay, here, let's do this. Yeah, no, let's just do a loaded red die. Hear about this. So we've got a loaded die. And it comes up, the probability distribution is the following. So what do you remember what we did on Tuesday? What did I say? It was like 11/12 if X equals 1. And then, oh, no, I don't want to do this number because I feel like I've used that somewhere. 2/3 if X is equal to 1, and then 1/15 if X is equal to 2, 3, 4, 5, or 6. Okay, let's do this. So here's my loaded die, right? And you can see 1 comes up way more than any other number, okay? And let's say we play the following game. This game is gonna cost you $1 to play. Or let's say it costs you $2 to play, okay? So it costs $2 to play the following game. And the game is the following. You roll the die, whatever number comes up, that's how much money you win. Roll the die, win however much money the die shows. Okay? If you only gave 2/3, yeah. So basically, what's the remaining probability? The remaining probability is 1/3, and that has to be evenly distributed over the other 5 possibilities. So I took 1/3, divided it by 5, and that gave me 1/15. Right. Okay. So does everyone understand the game? So you pay me $2. I'm going to let you roll my die. If the die comes up 5, I'm going to give you $5 back. Okay. If the die comes up 1, I'm only going to give you $1. So you lost $1. Does that make sense? And what I could ask you is, what is the expected value of rolling the die? Like how much money are you going to win on average if you play this game enough? So are the rules clear? Good. Okay. Okay, so technically what we have here, what we need to do is we need to do a random variable. And you don't, like when you solve the problem, you don't necessarily have to do a random variable, but I think it probably doesn't hurt. So what we need to do is a random variable which tells us how much money we win depending on what the dice roll is. Okay, so if little x is the dice roll, let's say let big X be how much money we win. Okay, so what is big X of 1? So if you roll a 1, how much money do you win? Like what's your net earnings? What are your winnings? -$1, perfect. If you roll a 2, 0. Okay, I think you all get the idea, right? If you roll a 3, you get a 1. If you roll a 4, you win $2. If you roll a 5, you get $3. And if you roll a 6, you get $4, right? Everyone agrees? Like this is how it works. So the expected value is the probability of each event occurring multiplied by the outcome of that event, right? And the way that we write this is with the scary sigma notation. Hold on, stupid pen died again. So again, if you don't want to remember this thing that has sigma notation in it, all it is a weighted average. Okay, so what you're doing is you're multiplying the outcome by the probability that the outcome happens. All right, so the expected value of this random variable is the probability over all possible outcomes, right? So in this case, R is -1, 0, 1, 2, 3, 4, right? It's all these things. Okay. Yeah, stupid pen. I feel like I said a lot. Okay, so that's what capital R is, of little r times the probability that x is equal to little r. It's not the sample space. The sample space, it depends on what you mean. The sample space of the roll is just 1, 2, 3, 4, 5, 6. This is the range of the random variable. And Jacob, I totally get you. I remember when I was learning probability, I was just like, these are stupid words. I don't understand what they mean, but they're technically different. So in some sense, Jacob, you're right. You could think about this as the sample space if you wanted to. And then what we're going to say is what is the probability of each of these outcomes. So if you wanted to internalize it like that, that's not a terrible way of doing it. But if you go and you take more probability theory, somebody will probably yell at you for that. Right. Okay. So Curdy, what we're saying is, like, what I'm going to do here is I'm going to run through these things. So I'm going to do -1 times the probability that my outcome was -1, plus 0 times the probability that I won $0, plus 1 times the probability that I win $1, plus 2 times the probability that I win $2, plus 3 times the probability that I win $3, plus 4 times the probability that I win $4. Does that make sense? Right. And Jacob, sorry, I don't know if I answered the would you have to specify question. So what would you have to specify what? Like what big R was? You should definitely say what big R is. I mean, in this case, the range is obvious. I would say it. Again, so strictly speaking, you probably don't want to call this a sample space, but what you could say is the collection of possible outcomes of the random variable. Like that's how you would properly say it. If you just said the collection of outcomes, that would be okay. Now, is everyone okay with like why this actually hopefully makes sense? Like I'm hoping that this isn't like a weird thing, right? In some sense, it's just a weighted average where, you know, if all of these things were, if the probability of all of these events were equal, it would just be what is the average of these numbers, right? Because there's, you know, 6 outcomes, you would add them all up and you divide them by 6. So it would just be the average. So what we're doing though is we're multiplying them by the probability that each event occurs. That's just a weighted average, right? Where you prescribe more weight to something that's more likely to happen. Okay, so what we're going to do now, so the probability of a -1, so what's the probability that I lose $1? Okay, so yeah, okay, so here's the important point. Exactly, it's 2/3. So Jacob, does that make sense? Why? Like, because we're not necessarily trying to isolate for the weighted die. It's like when you compute the probability, like when you roll 2 dice, the weighted die will show up in computing what the probability of each event is. Here, we'll do an example of that in a second. You're good with 2/3 here? Not necessarily. No, I don't think so. So you're saying you could, but okay, here, let me make sure. Could you finish this question from here? Like, and then the issue is just how to use the loaded die, like how to compute the probability of the loaded die. Sorry, that should be a plus. Okay, so this would be the answer, right? And somebody, okay, cool. So everyone could do this. So your problem, I think, yeah, your question seems to be a little bit different, which is again, so let's say we have this loaded die here. Let's copy that. Okay, and let's say this is the red die, and again, the blue die is fair. Right? So if you want to compute the probability of the event that, you know, so you roll both die, right? Roll red and blue. So the probability that you get a 5-4 out is, and let's say this is red, blue, is PR5 times probability of blue 4, right? And the probability of a red 5 is 1/15 times the probability of a blue 4 is 1/6. Yeah, exactly. And so that's where the loaded die comes in. So does that make sense? So you're not trying to isolate for a loaded die. And yeah, you would do that for each. Now in practice, what you would say, right? Like you wouldn't actually do it for, like there's 36 outcomes. So you don't want to do it for every outcome, right? So what you would say is like, oh, look, the probability in this case, you can basically break it into cases of where the red die is 1 and where the red die is not 1, right? So I'd say something like, look, the probability of a 1 times anything is, 2/3 times 1/6. And then the probability of anything else, yx, where y is, 2, 3. You can put that into words if you don't want to write it mathematically, is 1/15 times 1/6, right? Like don't do way too much work there, right? Like just, no, I'm not doing any conditional probability here. I'm just saying, like, instead of writing it out for all 36 cases, you're going to notice that there's really only 2 probabilities that could come out. So if you want, start writing it out for all 36 cases, just as a learning sort of thing. And you'll very quickly see like, oh, wow, most of these are the same. And the only thing that it depends on is whether the red die is 1 or whether it's not 1. So in some sense, it becomes much quicker to compute the probabilities if you do it that way. Though I think, like, again, the question uses a coin, right? But same sort of thing, right? In that case, whether it's heads or whether it's tails will change the probability. But because TJ's coin is fair, that doesn't really affect the probabilities at all. The only thing that matters is Rita's coin and whether that comes up heads or tails, right? That's the only thing that's really going to change the probabilities. Okay, so are you good? Sure, I'll try and remember. I'm gonna go, head out for a walk with my wife tonight, and I'm gonna try and let it compile while I'm gone, and then hopefully when I come home, I will remember, and that will be my goal. All right. Okay. So I'll try and remember to do that tonight. But either way, we're talking about probably an hour and a half to 2 hours, just because the bloody thing takes an hour to compile it at best. Okay. No problem. Hopefully that helped everyone. No problem. Yeah, hopefully that helped. And like I said, I'll try and get this video up. It seems like a lot of people really want it. So is it 1/6 because there's 6? Yeah, Emma, in the case of the fair die, it's 1/6 because the blue dice was fair. There were 6 outcomes and they were all equally probable. So that's exactly why it was 1/6. Okay. Yeah, no problem, everyone. Have a great weekend. I will see you all on Tuesday, hopefully. Okay. See you around.